Welcome back to this lecture series. Previous lecture, we have discussed how the boundary layer formation taking place over the flat surface. Now we'll discuss how the boundary layer formation taking place and the characteristics associated with this formation when the flow is taking place over the non-flat surface. Uh, these are some applications. Non-flat surface, the common examples of non-flat surface is sphere and cylinder. So these are some cases where the flow of either one is moving, either that object is moving or the fluid is moving. So this is a smooth ball, or maybe called as a cricket ball or golf ball. Its movement with the still air, or we can analyze with the scope of analysis why. From this analysis, we will come to know why there are dimples on the golf ball, why the cricket ball is smooth, what is the use of spin, what is the use of the seam for spinning, how the spinning does generally with the help of this spin seam. Then the flow over a bundle of tubes, maybe in many heat exchangers you'll come across such kind of flow. This is a CFD analysis of flow over a bundle of tubes or sphere. Then this is a heat exchanger we can call a shell and tube heat exchanger, where the bundle of tubes appears and the flow is taking place over this in zigzag manner. These are practical examples where the flow over this non-flat surface is taking place. Another example is this evaporative condenser, where the flow of air is taking place over these tube bundles. This is our radiator fan or tube or fin tube heat exchangers, which are used in radiators as well as on air conditioners, window air conditioners, air conditioners. So all these are the cases where the external flow is taking place over a non-flat surface. So at the micro level, again, because these are some external agencies used to force the fluid over the surfaces. So some resistance is there from these surfaces. So how to minimize these resistances? Again, for that, the flow analysis is essential over this sphere or cylinder. Obviously, most of the external flow analysis, the computational fluid dynamic theory is extensively used because it is quite mature in external flow. And most of the complicated flow analysis, we can easily visualize the flow over external surface with the help of CFD analysis. Most of the CFD results I have exhibited in previous slide also. So external flow, the approach of analysis is computational in most of the cases. So first of all, see what is this concept of boundary layer separation. Generally, if the fluid is flowing over a flat surface or over external body, there are three types of forces acting on it. Inertia force because of its velocity, because this is a mechanical force, or it is mechanically driven systems most of the cases. The mechanical draft is there. So some mechanical agencies like fan, pump, blower, these are used to force the air over the surface, or vice versa. In that case, the air is moving and the object is, air is stationary and the object is moving. That cases are there. But under these cases, three types of forces generally exist: inertia force, viscous force, and pressure force. Especially for flow or a flat surface, the pressure gradient doesn't exist because this is a free flow, and at both end, because at leading edge or rear edge we have seen. So there is no pressure gradient. As there is no pressure gradient, means no pressure force exists. But for non-flat surface, pressure force also exists. So all these forces are there. Now, depending upon the magnitude of these forces, there is a possibility of the flow variation. Suppose when the pressure gradient in the direction of flow is negative, means there is continuously decrease in pressure. It happens generally in pipe flow, it happens, but in external flow, if there is a decrease in pressure gradient. Then what will happen when the pressure, that is, when the pressure decreases in the direction of flow? The pressure decreases according to Bernoulli's equation. As pressure decreases, velocity increases. Means fluid accelerates. And in this case, the pressure force and inertia force add together and jointly tend to reduce the effect of viscous forces in the boundary layer. So generally, the pressure forces and inertia forces, they are generally acting along the direction of flow, and viscous force acts opposite to the direction of flow. So when pressure gradient is negative, the pressure force is also acting because there is driving force toward the direction, because pressure at the upstream is greater than pressure at the downstream. So pressure force acting along the direction of force, and it assists the inertia force. And so both together they resist the viscous forces. And this results in the decrease in thickness of the boundary layer in the direction of flow, as a consequence of which there are low losses and high efficiencies in the accelerating flow. This is a desirable thing. When the flow is accelerating, so the thickness decreases, means there is less drag force, the fluid is accelerating. So two forces are dominant along the direction of flow, means they are not resisting the flow, because the resisting flow is only viscous force, and they are dominant over the viscous force. The fluid accelerates, and consequently the thickness, viscous thickness, or the boundary layer thickness is reduced. That is the case. On the other hand, when the pressure increases in the direction of flow, that means delta P by delta X is greater than zero. That what it indicates means pressure at the outlet is greater than pressure at the inlet. So in this particular case, the pressure force assists the viscous force, and only the inertia force acting along the direction of flow, and pressure force and viscous force, they are acting opposite to the direction of force. So what will happen? The pressure forces act opposite to the direction of flow and further increases the retarding effect of the viscous force. So both viscous forces and pressure forces, they retard the motion. And subsequently, the thickness of the boundary layer increases rapidly in the direction of flow. And if these forces act over a long stretch, the boundary layer gets separated from the surface and moves into the mainstream. This phenomenon is called as separation. And the point of the body at which the boundary layer is on the verge of separation from the surface is called as a point of separation. So this is the concept which is because of the relative motion of these two forces. So generally, the relative motion or the magnitude of inertia force and viscous force are most of the cases are same. Only because of the magnitude of pressure gradient, whether the pressure gradient is zero, if it is positive or zero or negative. Because of this pressure gradient, and in non-flat surface, this pressure gradient exists. Because of this existence of positive pressure gradient, there is a possibility of separation. So it is always recommended to avoid this positive pressure gradient. So we will quickly go through these videos. So how uh, we can visualize this type of flow. What type of flow we can visualize? Here it is a laminar flow. Here it is a turbulent flow. We can visualize how the flow behaves, how the separation is taking place when the flow is laminar or turbulent. It will take some time, but it will definitely happen. And from this, we will come to know, suppose this is a laminar flow. When the flow is taking place, this is a layer. When the flow is taking place over the surface. So how it will assist, how see here, the turbulent flow cases, there are large eddies are formed and the separation is taking place. So here it is a separation is taking place. So, and the large eddies are formed, and this this is because of the positive pressure gradient. Here the fluid is accelerating, but here after that the fluid becomes decelerate, and then the retarding motion is taking place. So reversal flow is taking place. While in laminar flow, because the velocity is very low, there is a smooth transition of this layer happening here. So fluid particles are easily processed, so no retardation is taking place. But in case of turbulent flow, we can visualize here there is a retardation. So this is a wake region of low pressure because of pressure gradient. And because of this, uh, there are large eddies are formed and the reversal flow is taking place. So this is about the flow over sphere in both cases, and the laminar flow is taking place and turbulent flow is taking place. Similarly, we will now discuss the boundary layer separation over sphere or cylinder. Now we consider a flow of fluid over a curved surface. I had shown in figure. This is a curved surface. It may be a surface of sphere or it may be a surface of cylinder. As the fluid flows around the surface, now if we see, suppose here, if we draw the line where most of the cases the boundary layer or the velocity above this is reaches, the boundary layer effects are negligible above it. Now this is a flow passage. If you see in this particular passage, if you see as the fluid flows around the surface, the area of the flow decreases. So here the area, see the area here, so it decreases. So it is accelerated over the left hand side until a point B is reached. The velocity just outside the boundary is maximum and the pressure is minimum. So you can see here, this is the variation of pressure. And so if you see, if the fluid is taking place, this is suppose a flow section, and beyond this, the velocity is maximum. And initially, the flow passage is converging, so the fluid accelerates. So these are the positive velocity gradient exist here, and the boundary layer thickness is more or less remains constant in this particular zone. Because fluid is acceleration, boundary layer tends to decrease, but velocity increases, velocity tends to increase the boundary layer. So that the net result is zero. So the boundary layer thickness remains uniform here. So here the point B is reached, where we can say the pressure is minimum because this is the lowest cross flow passage. You can say lowest flow passage, and gradually the pressure decreases. So this is a negative pressure gradient, and which causes a positive effect because here both inertia force and pressure force assist the flow. That's why there is a limit on growth of boundary layer up to point B. Thus, from A to B, the pressure gradient is negative, and as long as the pressure gradient is negative, the entire boundary layer moves forward. So it moves forward. On the other hand, the beyond point B, along the region B, C, let me beyond point B, that is along the region B, C, D, E, the area of the flow increases. So if you see this particular area, the flow passage increases, and hence the velocity of flow decreases. Velocity of flow decreases due to decrease of velocity. Due to decrease of this velocity, the pressure increases because as the velocity decreases according to Bernoulli's equation or law of conservation, pressure increases and in the direction of flow. Thus, hence the pressure gradient. Suppose that if you measure the pressure here and pressure here, so here the pressure is more than pressure at B, so the pressure gradient is positive. Pressure gradient is P2 minus P1, that is positive. So the pressure gradient is positive, that is, this is a mistake, that is dabba P is positive, that is dabba P by dabba X is positive. The value of the velocity gradient du by dy at the boundary is 0. So here you can see this is the point at the value of du by dy at the boundary is 0 at that particular point, because here the boundary layer thickness it continuously increases because of decreasing velocity, increasing pressure. So in this particular zone, we can see the pressure force assists the viscous force. So there is a retardation of the fluid particles. And so the boundary layer growth is sudden. There is a sudden increase or growth of the boundary layer thickness. And then the point C is reached where the velocity gradient is zero. That is W by W is zero. And this point is called as a separation point. That is, the boundary layer starts separating from this particular point. You can see the boundary layer starts separating from this particular point because uh, further retardation of flow near the surface is physically impossible. Large turbulent eddies are formed downstream of the separation point that we have seen in previous videos. The large eddies are formed. The distributed region in which the eddies are formed is called as a turbulent wake. So in this particular zone, the turbulent wake region is formed. And if it is further increased, then there is a possibility of reversal flow. You can see here, the flow is reversed because the velocity is negative in this particular zone. Here, the magnitude of that reverse negative velocity further increases, and then the eddies are formed in this particular zone. And so from C point, there are heavy losses occurred because of this positive pressure gradient, and this positive pressure gradient becomes adverse, and the reversal flow is taking place in this particular zone. This is a concept of boundary layer over a sphere or cylinder that we already discussed that we already observed in the previous videos. The, it flows over a spherical surface, how the disturbances are there at the downstream. And that turbulent wake region also we have observed. The flow separation mainly depends on the factors, that is, which is the curvature of the surface, what should be the Reynolds number of the flow. So we have seen both videos, laminar flow and turbulent flow. So in case of laminar flow, we haven't seen any separation taking place there. Only at the end downstream, the slight separation taking place, but at the turbulent flow, immediately at the mid only the separation taking place. So means turbulent flow Reynolds number is high. So it depends on Reynolds number as well. Then the roughness of the surface also plays an important role because due to roughness also it breaks the laminar sublayer. So the turbulence is created. So it breaks the boundary layer as well. So it is sometimes desirable to have a roughness. The velocity gradient for a given velocity profile exhibit the following characteristics for the flow: remain attached, get detached, or on the verge of separation. So we have seen in the previous line when there is a positive velocity gradient, then the flow remains attached. There will not be any separation taking place. When it is zero, then it is on the verge of separation. And when the velocity gradient is negative, then the flow separates. That we have seen in previous. So that flow characteristics, that is whether the flow is attached, detached, or on the verge of separation, that we can easily recognize with the help of the velocity gradient at y is equal to 0, that is at the surface. So the boundary layer separation is not at all a desirable. It is an unstable process, inefficient process, and it enables a large losses due to applicable aiding regions. So it is always necessary to avoid this separation through various methods that we are also going to discuss. So before that, we'll see how to solve the numericals on separation, how to investigate whether the flow is attached or detached or on the verge of separation with the help of the equations given, that is a non-dimensional velocity gradient. So let us see for the following velocity profiles, determine whether the flow is attached or detached or on the verge of separation. This is non-dimensional velocity gradient. So U is the local velocity, capital U is the mainstream velocity, Y is the distance of small u, and U is the boundary layer thickness. So these are three velocity profile equations are given in non-dimensional. And we have to recognize whether the flow is attached, detached, or on the verge of separation in all three cases. So first case, we will see that is first velocity profile is given or equation is given. Now we have seen in previous the velocity gradient with respect to y is equal to 0. If it is positive, negative, and 0, then it exhibits some characteristics. Suppose, so we differentiate, if we take only a small u on one side, other terms on right hand side, and we differentiate this u with respect to y and equating to 0. So dabba u by dabba y, that is u into bracket 2 into 1 upon delta minus 2y into 1 upon delta square. So if we put y is equal to 0, so we get dabba u by dabba y at y is equal to 0, that is 2u by delta. It's a positive value. So if w by y is positive, that means flow is attached. So similarly, we check other equation whether the flow is attached or detached. Similar process, you take one side, other terms, other sides, differentiating with respect to y. We get these are simple differential equations. W by y, then put y is equal to 0 in the above equation and check what is the value of w by y is equal to 0. In this case, it comes negative. That means flow is detached. Third case, again the similar procedure. We rearrange the equations. So u is equal to this. Differentiating with respect to y, and putting the value of y is equal to 0. In this case, in every term there is y, so this is equal to 0. That means the flow is just on the verge of separation. It's on the verge of separation. So this way also we can recognize whether the flow is attached, detached, or on the verge of separation. Because some small numericals can be asked in MCQ exam also. So with the help of the equation, further we have to do slight mathematics, that is only differentiation of u with respect to y and equating to 0, and check whether the w by y at y is equal to 0, whether it comes 0, positive or negative. And based on that, you can recognize the condition, whether it is attached, detached, or on the verge of separation. So this is the condition which can be used for the situation. It's attached, detached, or on the verge of separation. So separation occurs in most of the cases like non-uniform cross-section, that is diffuser. There is also internal flow. Also, there is a possibility of sudden enlargement in cross section. There is a possibility of separation and error. So, in order to avoid that, generally the gradual enlargement is preferred. An open channel transition where there is a sudden enlargement, then the flow near the boundary is already separated. So you might have experienced that. In pumps also, there is a possibility, especially at the impeller outlet, there is a possibility of then fans or turbine blade, wind turbine blade, where how the separation is taking place that we can analyze with the help of COD. Aerofoil sections where how the flow separation taking place. So all these cases, the separation analysis, that's why the flow pattern study is carried out in wind tunnel in order to get these points, that is where the pressure is maximum, that is called as the stagnation point, where the separation occurs, and what is the area of the wake region. That wake region is, this is the area of wake region. We can say this is the area, there is almost zero wake region. Large wake region is not at all desirable because it increases the drag force. There are some methods of preventing this separation of boundary layer. So some of the methods we will list here. Following are some of the methods generally adopted to retard or arrest the flow separation. That is streamlining the shapes, then tripping the boundary layers from laminar to turbulent by providing surface roughness, and so we can minimize the separation. Then sucking the retarded flow, we can suck the flow and keep the flow attached. Then injecting a high velocity fluid in the boundary layer in order to increase the inertia force. Then providing a slots near the leading edge. That way also we can diverting the flow, we can avoid the boundary layer separation. Then guidance of flow in a confined passage and providing a rotating cylinder near the leading edge. Uh, Energizing the flow by introducing optimum amount of swirl in the incoming flow. That is a mechanical way we can say. So these are the almost 8 techniques we have listed for preventing the separation of boundary layer. Few of those techniques we will discuss. That motion of solid boundary by rotating a circular cylinder lying along the direction of flow, lying in stream of fluid, so that the upper side of the cylinder, where the fluid as well as cylinder moves in the same direction, the boundary layer doesn't form. And however, the lower side of the cylinder, where the fluid motion is opposite to that of cylinder, separation would occur. So here there is a possibility of separation, but we can extend the separation instead of causing the separation here. Because of this rotation of cylinder, we can prolong this separation, and so we can minimize the losses. Acceleration of the fluid in the boundary layer. So here by injecting some fluids, the method of controlling separation consists of supplying additional energy to the particle of the fluid which are being retarded in the boundary layer. This may be achieved either by injecting the fluid into the region of boundary layer from the interior of the body with the help of some available devices as shown in figure, or by diverting a portion of the fluid of the mainstream from the region of the high pressure to suppose this is a region of high pressure and this is a region of low pressure. So by diverting some portion of the mainstream from the region, that is by making a slot, then this way also we can prolonging the boundary layer. So this is acceleration of the fluid by injecting or by making diverting the flow. So in this region there is a high pressure, in this low pressure. So easily high pressure fluid flows through this passage, and here the fluid accelerates and the separation can be prolonged. Then the suction of the fluid. So if we place a vacuum pump or some pump here, so the suction of the fluid to keep this layer attached. In this method, slow moving fluids in the boundary layer is removed by suction through slots or through a porous surface as shown in figure. Or we can say streamlining of the body, to make the body streamlining. So we can minimize almost the separation here. So very small wake region we can see here. So by use of suitable shape of the body, so along the streamline we can shape the body. The point of transition of the boundary layer from laminar to turbulent flow can be moved downstream, which results in reduction of the skin friction drag. And furthermore, by streamlining of body shapes, the separation may be limited. These are some techniques where we can eliminate the separation completely, or we can prolong the separation so that the total drag force can be minimized. Because the separation, if it causes the opposite force on the downstream. So there is a it further reduces the motion of that particular fluid. So that's why the separation, even if we prolong the separation, then the wake region decreases considerably. Now you can see here, the very small wake region appears. That is so if the separation occurs here, then the wake region is more. So larger the wake region, more is the opposite force and more is the resistance of it. So that's why the separation is not at all desirable. And that's why these are some methods we have discussed to control the separation. That's it from this particular session. At the end of this particular session, you will be able to explain the concept of boundary layer separation. Then you could be able to discuss the flow over sphere or cylinder and how the velocity profiles vary when the flow is taking place over sphere or cylinder. That we have plotted the velocity distribution at A, B, C, D, E, and how we can say where the velocity gradient is positive, where the velocity gradient is negative, where the velocity gradient is uh, negative or reversal flow is taking place, or where the velocity gradient is zero. So that all part we can discuss when we will be able to discuss when the flow over sphere or cylinder is taking place. We will be able to investigate the flow, whether it is attached, detached, or on the verge of separation. If we know velocity distribution equation, uh, local velocity distribution equation in non-dimensional form, so differentiating that with respect to y and at y is equal to 0, and with the help of the value of dabba u by dabba y at y is equal to 0, we can recognize whether the flow is attached, detached, or on the verge of separation. The positive value of dabba u by dabba y at y is equal to 0, flow is attached. Negative value, flow is detached. And if w by y at y is equal to 0 is 0, then the flow is on the verge of separation. Then you could be able to discuss the methods of controlling the boundary layer separation as well. There are 8 methods we have listed, and few of them we can discuss with the help of diagram as well. That's it from this particular session. In these 2 sessions, we have discussed that how the boundary layer formation taking place over a flat surface, boundary layer separation or boundary layer formation taking place over non-flat surface like sphere and cylinder. And what are the thicknesses associated with the boundary layer, like displacement thickness, momentum thickness, and energy thickness? And what is the importance of these thicknesses in practice? These thicknesses are nothing but not the actual physical thickness. These are the amount of losses encountered, relevant losses, that amount of loss of mass flow rate, amount of loss of momentum, amount of loss of energy. Like that. With this, so we have completed this session. Thank you very much.